We can think of a uniform disk as essentially a two-dimensional or planar object, so its thickness is negligible. Uniform means that the mass is uniformly or evenly distributed throughout this disk. So the center of mass is at the geometrical center of this disk. Okay, so let's imagine an angle, an incline of angle theta that is perfectly smooth. So the surfaces of the disk and the incline are smooth. So that means that we have no friction force acting on the disk. Now in red I'm showing the two forces acting on the disk. We have its weight mg, where its mass is m, and we have a normal force, a contact force on the disk, which is normal or perpendicular to the surface of contact. Okay, so as a reminder, I'll just run through this again. Now, to find the magnitude of the normal force, we have to consider the angle between a line perpendicular to the incline and this vertical line. Well, this pair of lines is perpendicular to this pair of lines here. So that tells us that the angle between both of these pairs of lines is the same. So the angle in here is the angle of the incline. So the component of the weight force perpendicular to the incline is the side adjacent to theta in this right angle triangle. So it's mg times cos of theta. Since the disk has no acceleration perpendicular to the incline, this component of the weight vector must have the same magnitude as the contact force. So the normal or contact force is mg cos theta. What's the resultant force on this disk? Well, we want to get the vector sum of these two red vectors, but the components perpendicular to the incline add to 0. So if we consider the components parallel to the incline, we'll have the resultant mg cos theta. The normal force has no component parallel to the incline, whereas mg has this component here which is parallel to the incline. It's opposite theta in this right angle triangle. So this vector is mg sin theta, and that's actually the resultant force on the disk. So the resultant force is parallel to this incline. Its magnitude is mg sin theta, and of course we can see the direction is obviously down the incline. Now by Newton's second law, the magnitude of the resultant force is mass times acceleration, so A is g sin theta. So we've seen this kind of thing before when we dealt with a particle of mass m on an incline of angle theta. We saw that the acceleration does not depend on the mass. Okay, m doesn't appear in this. The acceleration A depends on angle theta. So as sine theta goes up, the acceleration goes up. Well, when angle theta goes up, sine theta goes up. Okay, the sine function increases for acute angles theta. So this formula makes sense. Okay, if we make the incline steeper, the acceleration of the particle down the incline increases. Now, if the surfaces were rough, okay, not perfectly smooth, what would happen? What other forces would we see? Well, as the mass moves down the incline, it would push on the incline in this direction. Okay, if the forces were rough, the disk would somehow dig into this incline. But of course, if the disk pushes on the incline in this direction, Newton's third law tells us that the incline would have to push back on the disk with an equal force. Okay, force of equal magnitude. So these are equal but opposite vectors. Okay, so that's not happening here. We'll get to that situation soon. Okay, so does this disk turn as it accelerates down the incline? Well, for the disk to turn about its center, we would have to have an external torque on the disk about the center. So we imagine that the disk is just placed on the incline, it's not spinning already. So for it to spin, to turn around the center, an external torque about the center would have to be applied. But look at the two forces acting on this disk. Their lines of action pass through the center. So if we want to consider the sum of the torques sum of external torques on this disk about the center, we would have to take each of the two forces, mg, say let's start with mg, get its torque, okay, but the distance of c to the line of action of mg is 0, so we multiply the magnitude by the distance to the distance of the center of mass to the line of action of the force, and we'd have to do the same for the normal force. But the normal force acts perpendicular to the surface of contact, so that means that its line of action passes through the center. So the torque due to the normal force is the magnitude of the normal force multiplied by the perpendicular distance of c to its line of action, which is 0. So we just get 0 for that. From previous videos we know that the principle of angular momentum says that the sum of all the external torques about a point C is the moment of inertia of the object about the point C times the angular acceleration alpha. But if this is equal to 0, it tells us that alpha must be 0, because I is certainly not 0. I is a positive number. Alpha, remember, is the second derivative of the angular displacement theta with respect to time. So that second derivative is 0. This is the angular acceleration. So we have a situation here that's analogous to Newton's first law. As a reminder, Newton's first law tells us that if the acceleration is 0, then the resultant force acting on the object is 0. Okay, so here the angular acceleration is 0, so the resultant torque is 0. We're not talking about resultant force, we're talking about resultant external torque. So from this we see that the first derivative must be a constant, it must be fixed. But this is the angular velocity, also called omega. Alright, you see, if omega is constant, then if we differentiate, we get 0. If we differentiate a constant with respect to time, we get 0. It doesn't change with time. So if omega had some value to begin with, when we place the disk on the incline, it will retain that value. That value will be constant as the disk moves down the incline. So for example, if the disk was not spinning to begin with, so the disk is placed on the incline with 0 angular velocity, well, the disk's angular velocity will remain at 0. So we get the somewhat strange looking result that this disk will move down the incline without turning. So this point on the disk will always remain in contact with the incline. Of course, that's something we never really see in real life because we don't have perfectly smooth surfaces. Now let's look at the case involving friction. So if these were the only two forces acting on the disk, of course the disk would start to move down the incline. But since the disk digs into this incline to some extent, the disk will push on the incline in this direction. And by Newton's third law, we will have an equal but opposite force on the disk. Equal in magnitude but opposite in direction. So this is the friction force. So I'll use the small f to denote that. Now later on in this video I'll discuss more about this friction force in relation to the friction force on a particle of mass m. So a particle that has the same mass as the disk. But for now we'll say that this friction force is constant, and it's actually responsible for turning this disk about its center of mass. It's the only force that's responsible for that turning, because we saw that these two forces, the normal and weight, have no torque about the center of mass, no turning effect about the center of mass. So now we go back to the principle of angular momentum and consider the sum of all the external torques acting on the disk about the point C. Well, look at F. What do we have to do to get the torque due to the friction force F about the point C? We have to multiply the perpendicular distance of C to the line of action of F, that's the radius of the circle, by the magnitude of F. So here we're just getting the magnitudes of the sum of the external torques we want to emphasize that, we could just put vertical lines here, getting the magnitude. So it's r times f, or fr. So we know what that is. It's the moment of inertia of the disk about the point C times the angular acceleration alpha. So we know that the disk is going to roll down this incline with some acceleration alpha, or sorry, not alpha, but a. And a is going to be related to alpha, provided that this disk rolls without slipping down this incline. So we're going to just discuss that situation of a disk rolling without slipping along a surface. So here I have a disk of radius r on this surface. At some time it's here, and at some later time it's over here. So let's consider the distance travelled by this disk. Well, we just get the distance between the points contact at those two times with the ground. Okay, let's suppose that this distance is x. So how do we relate that to the angle through which this disk has turned? Well, if this disk rolls without slipping, okay, disk is moving in this direction, of course. If it rolls without slipping, then this amount of the disk has made contact with the ground. So this distance is the same as x. So this arc length is x. Suppose that the angular displacement is theta. So that's the angle through which the wheel has turned as it moved the distance x. Now we measure theta in radians, of course. Well, the length of an arc subtended by theta is the radius times theta. So x is r times theta. Our angular acceleration alpha is d2 theta dt2, the second derivative of theta. So we can relate that rate of change of theta to the rate of change of distance travelled. Distance x will be the distance down the incline, say. You see that r doesn't change, of course, the radius is fixed, but theta changes. When x changes, theta changes. So if we want to find out the rate of change of x with respect to time, we just differentiate r times theta with respect to time. So r is just a constant multiple, so we're differentiating a constant times a function of time. So it's just r times the derivative of theta. Okay, so r is just a number sitting in front of theta. We just take it out and differentiate theta. If we differentiate this thing again, well, this derivative here is the acceleration of the disk along the surface, and r is just a constant, and now we get the angular acceleration. So I just differentiated the speed with respect to time, and we have to differentiate the angular speed with respect to time to get the angular acceleration. But this quantity is also denoted by a, so this, I'm trying to relate it to this picture here. We want the acceleration of the disk down the incline. So we can see that a is just r times alpha. So that means that we can replace this thing here, alpha, with a over r. So from that we can write down the friction force. It's the moment of inertia of a uniform disk of radius r about the centre of mass times the acceleration of the disk down the incline divided by the radius squared. Now later on I will work this thing out more fully, of course, and I'll compare this to the friction force on a particle of mass m on the incline. But for now I want to get on and get a by looking at the resultant force on the disk. So here is the magnitude of the resultant force on this disk. So I'm taking directions down the incline as positive. So we have mgSinθ, as we would if there was no friction, but now we have to subtract the friction force, and we apply Newton's second law. So this is the mass times the magnitude of the acceleration. Now I plug this quantity here in for f, little f, and I want to solve for the acceleration. So I've brought this term over and added to ma. I've written it here on the left hand side, factorized out the a, so now we just divide. Now the next thing that we do, of course, is plug in for the moment of inertia of a uniform disk about its centre of mass. We know that that's a half its mass times its radius squared. Now, notice that the mass disappears. So the acceleration of the uniform disk is independent of the mass. Notice also that the radius disappears. So the acceleration is independent of the size of the disk. So it doesn't matter what the mass is or the radius, the acceleration is constant. So what have we got here? We have a 1 here. Well, we have 1 plus half in the denominator. So we have g sine theta divided by 3 halves. Not surprisingly, this acceleration is less than the acceleration of the disk when there is no friction. Now, let's get the magnitude of this frictional force. So I'm just plugging into this formula that we saw earlier. The acceleration is what we just got, of course. And we divide by r squared. We have 2 times 3 halves here. So we end up with 1/3 mg sine theta. Let's compare the friction force on a particle of mass m. So the particle has the same mass as the disk. So let's consider a particle on a slope, on an incline. But we're going to make the incline progressively steeper. We're going to increase angle theta. Okay, so it's got the same mass. Now I won't indicate the weight or the normal force, but what I will indicate is the direction of the resultant force if there's no friction. So if there's no friction, we know that the resultant force is magnitude mg sine theta. Actually, I'll just write it in here. Now, that's if there's no friction. But what do we know about friction? The friction force starts off at 0. At 0, you know, if the particle was just sitting here on the horizontal, well, of course, then we'd have no force to the particle would just be sitting here. The resultant force on it would be 0 if there's no friction. And the friction force would be 0, obviously. But if we increase the incline by a small angle theta, what's going to happen is we're going to get this force mg sine theta appearing, which is the force that would exist if there's no friction, but we would have a force counterbalancing it. That's the force of friction. So F lies between 0 and actually some maximum value. We can imagine increasing the incline further. So now mg sine theta is even greater. You see, as theta increases, the sine of theta will increase, you know, for an acute angle theta, which means, of course, if sine theta increases, then the resultant force in the absence of friction increases. Okay, but the friction force will keep on increasing to counterbalance that force. But there's going to come a point, of course, we know from the section on friction that, you know, we keep on increasing mg sine theta by increasing theta. So now we have an even greater mg sine theta. But the friction force can't keep up, you know, reaches some maximum. Let's suppose the maximum is reached at this position. Well, what is the maximum friction force? Well, we know that it's proportional to the normal force, the contact force between the particle and the incline. And that contact force is mg cos theta. It's proportional to mg cos theta. And the constant of proportionality is mu. That depends on the nature of the surfaces. So the maximum friction force is mu mg cos theta. Okay, so now at this point the particle is on the verge of slipping. So let's just I'll just move this out of the way and consider the situation where the particle is actually slipping. So let's consider a steeper incline, one like this. Now the particle is definitely slipping here. In this position, mg sine theta is considerable, but the friction force hasn't changed. The friction force is still mu times mg cos theta. Actually, I'll exaggerate this just to make it even clearer. So this is our mg sine theta. This is the force that we would have in the absence of friction, and here's our mu mg cos theta, and you can see that mg sine theta is greater than mu mg cos theta. Okay, in this situation here. So obviously the particle is sliding down the incline. So just to get back to this situation here where the mass is on the verge of slipping, these two forces are the same. This force is mgSinθ, this force is µmgcosθ. So in this position, the force on the particle due to the surface is at its maximum. Now the force on the disk to cause it to roll without slipping down this incline is 1/3 mgSinθ. So the incline has to be able to supply this force to the disk to cause it to roll without slipping. But what if the surfaces aren't rough enough? You know, the maximum force on this disk that the incline can supply to it is this quantity here. So I'm calling this quantity as the maximum. So it's µmgcosθ. Okay, so what if that force is less than the 1/3 mgSinθ that's needed to cause this to roll without slipping? Well, in that case, the disk will not roll without slipping. It will actually slip down the incline. Alright, so rearranging this, we see that if mu is less than 1/3 tan theta, then the surfaces aren't rough enough. The bigger mu is, the rougher the surfaces in general. If mu is 0, the surfaces are perfectly smooth. So again, the disk of course is pushing on the incline. But if the maximum that the disk can push on the incline is less than 1/3 mgSinθ, if the maximum force is less than 1/3 mgSinθ, then by Newton's third law, of course, the maximum force that the incline can push on the disk is 1/3 mgSinθ. Is less than 1/3 mgSinθ. So there isn't enough force to turn the disk. The force has to be at least equal to 1/3. The maximum friction force has to be at least equal to 1/3 mgSinθ. Note, of course, that the frictional force needed to turn the disk without slipping is independent of mu. So it doesn't matter how rough the surfaces are, as long as they're rough, of course. If they're not rough, then the disk won't turn at all. So it's always given by this thing. So it doesn't matter how small theta is, the disk will always roll down the incline. Now, well, that's not surprising. So it doesn't matter how rough the surfaces are or how small angle theta is, this quantity here will always be non-zero. So it'll have a torque, this force will have a torque about c causing the disk to turn.